Hello everyone and welcome back. I am Mr. Cobalt and today I'm going to be going over a problem regarding combustion analysis. So in my previous video I had gone over the steps on how to solve a combustion analysis problem. If you haven't watched that, you can go ahead and watch that. I will have it linked in the description section. But I will go through the steps in this problem. So here's a typical combustion analysis problem. It says, upon combustion, a compound containing only carbon and hydrogen produces 0.183 grams of carbon dioxide and 0.901 grams of water. And then they say, find the empirical formula. So what we need to do first is our goal is to get the moles of the elements, because once we get the moles of the elements that are in the compound, we can set up our pseudo-empirical formula and go from there. So the first part of this problem is getting those mole amounts. And the easy part about this problem is it tells you that the only thing in this compound is carbon and hydrogen. There's no oxygen, so we don't have to worry about finding out how much oxygen there is. So that saves us a couple of steps. In the next problem I'll go over, we will have to do those extra steps. But in this one, it's a little easier. So the first thing I need to do is I need to convert the gram amounts of water and carbon dioxide into moles. And the reason I want to do that is that then I can use the formula, the mole ratio in the formula, to go from moles of carbon dioxide to carbon and moles of water to hydrogen. Because the assumption is that all of the carbon and all the hydrogen went into these products. So the first thing I'm going to do is I'm going to take 1.83 grams of carbon dioxide. I'm going to use the molar mass of carbon dioxide, which comes out to be about 44.01 grams of carbon dioxide over under 1 mole. So 1 mole of carbon dioxide is on top. So grams cancel out. So now I have moles of carbon dioxide. So the next thing is I can do the same thing. I can now that I have moles of carbon dioxide, I can use the mole ratio in the formula to convert from moles of carbon dioxide to moles of carbon. So I can do that in another step. So I'm going to, instead of stopping and calculating, I need to get to moles of carbon anyway. So what I'm going to do is I'm going to now use the mole ratio. And the mole ratio of carbon dioxide to carbon is 1:1, because for every 1 mole of carbon dioxide, I get 1 mole of carbon, because every molecule of carbon dioxide has 1 atom of carbon. So I'm going to put 1 mole of carbon dioxide on the bottom, 1 mole of carbon on top. So now I have converted to moles of carbon. So now I can find the moles of carbon. So I will calculate that. So I have 1.83, and then I'm going to forget the 1, so divide by the top. So it's only 1's on top. So I'm going to divide that by 44.01. And that's, I only have 1, so that's it. So that's going to equal, and I get 0.04. So 0.04 158 moles of the carbon. Okay, and then I do the same thing for water. So now I'm going to set up the water. So I have 0.901 grams of water over 1. I'm going to use the molar mass to convert from grams to moles of water. So 18.016 grams of water on the bottom, 1 mole of water on top. So the grams cancel out. And now I can use the mole ratio in water. So here it's a 1 for every 1 molecule of water, it's 2 atoms of hydrogen. So it's a 1 to 2. So 1 mole of water on the bottom, 2 moles of hydrogen on top. So the moles of water cancel out. And now I have moles of hydrogen. So now I'm going to go ahead and calculate that out. So I have 0.901 times 2 divided by 18.016 equals, and there I get 0.1, like 000. So 000, there's a 2 at the end, I'll put that, moles of hydrogen. So now I have the moles of hydrogen and the moles of carbon, and those are the only 2 elements. Now, if I had oxygen, if I needed to find oxygen, what I would need to do is I would need to convert these to grams. So I would have to convert grams using the molar mass. And then I would subtract those grams from a given amount of my substance, right? So they would have to give me, like, what was the original amount of substance that was burned? And then I would subtract the grams of carbon and the grams of hydrogen from that to get my grams of oxygen that's left over from the sample. And then from there, I would convert grams of oxygen to moles of oxygen using the molar mass. And then I would have my moles of oxygen. But since there's no oxygen in the sample, I don't have to worry about those extra steps. So now I have all the moles that I want. So from this point on, it's just a normal empirical formula type problem. So now I take the molar amounts and I write my pseudo formula. So I'm going to have carbon with 0.04158, and then hydrogen with 0.10002. So this is the moles, these are the moles of carbon and hydrogen. So now I need to find the mole ratio between these two, so I'm going to divide by the smaller number, which is this one. So I divide both of these by the smallest number, 4158, and that's going to give me, this is going to give me a ratio between carbon and hydrogen, so 1 to something. So I'm going to divide this by 0.04158. And so when I calculate this, so this obviously is going to be 1, but this is going to be, if I divide that by 0.04158 equals, and that's going to give me a number, let me calculate, it says 2.405. Let me calculate that one more time just to make sure that is correct. So 0.10002, or we'll say 00, divided by 0.04158 equals, yeah, so we get 2.40. So then this is going to be carbon, which is, let's see, carbon, that's going to be 1. And then hydrogen, that's going to be 2.4. So it's really, really close to 2.4. Okay, so what we do there then is we have to then find out, okay, well, that 0.4, we can't round it, right? We can't round that to a 2. You might be tempted to say that's a 0.5 or round it to 0.5 and then multiply by 2, and you can't really do that. So we need to figure out what fraction it is. It's really close. It's 2.4 is too clean of a number. It's too far away from 2 to round to 2. It's too far from 0.5. So what do? Well, what is 0.4? What's the fraction for 0.4? 0.4 is the same as, I'll write it here, so 0.4 would be the same as, what is 0.4? That's going to be 3, no, that's going to be 2/5, right? So 2/5. So if you divide 2 by 5, you get 0.4. Well, that's the fraction that we have. So to get rid of that fraction, you're going to be multiplying by the denominator here. So you're going to multiply by 5. So then what we need to do is to get rid of that 0.4, we multiply by 0.5. So, or I'm sorry, by 5. So that means that 1 times 5 is going to be 5. So this is going to be your carbon 5. And then you're going to have 2.4 multiplied by 5. And that's going to give you 2 plus 10, so that's going to be 12. So hydrogen, that's going to be 12. So then that would be the empirical formula for this substance here. Okay? So this is, again, how you should attack or handle a combustion analysis problem. This one was easier since we didn't have oxygen. But once you got the oxygen, after you get the oxygen, it's just the same thing as setting up your empirical formula or your pseudo-empirical formula, and then figuring out what the actual empirical formula should be. Okay, I hope this is helpful. I'm going to go over another couple of examples, and so be tuned for that. Thank you for joining me. If you like this video, share this video, like the video. Make a comment in the comment section, and subscribe to the channel, as well as hit the notification bell so that way you can be notified for any new videos I put out. Thanks for joining me, and I'll see you next time.